I wanted to finish up our conversation of systems of equations by doing some graphing, which it bothers me that we never got into graphing of some of these systems and to see what we're doing when we actually put a matrix into reduced row echelon form and back substitute to see what we're doing geometrically. So I think that could be really helpful, but what's really bugging me is that there's an elephant in the room as far as all of this is concerned. So when we were developing our method, I just said kind of offhand that when you add that, if you have, say, two equations and you have a point that satisfies one of the equations and the same point satisfies another equation, when you add them together, you get a new equation and that point satisfies the new equation. I said there's proof for this, but it's really unsatisfying, so we're not going to go into it. And it's true, the proof is really unsatisfying, but it bugs me that we haven't proved it because our whole method hinges on that, right? If that's not true, then everything we just developed, it's on shaky ground, right? So I want to prove it, but I'm not just going to give you the proof because, like I said, it's really, you go, okay, and but so what I want to do is kind of work our way into it. We're going to see why it has to be true in order so that when we actually see the proof, it'll make a lot more sense. So we've talked about how when we say write a line in standard form, we can rearrange it, right? And this means if we could put it into y equals mx plus b, and we could have a line, we could draw the line, right? And this means the same thing as that. And I think we're all pretty much on the same page as that. Now, we also said that we could take that and multiply it through by any number, and you'll end up getting the same line. The way we've done that before is we just go and take a number, multiply it across, and then we just go solve for y, and we end up getting the exact same thing. But if we think about that another way, it's going to help us understand the proof that we're going to do. So that's what we're going to develop right now. We're going to say, okay, first off, let's just make sure we're on the same page here. One way of thinking about this line is as an input-output relation. When I plug in a 1 for x, I go 1 times 2, it's 2 minus 1 is 1, and we have a 1 for y. So that when x is 1 and y is 1, that's a point on that line. And we can see that, yeah, that means kind of the same thing as this, saying that the point 1, 1 is on this line because when I plug in a 1 for x, I get 2. I plug in a 1 for y, I have 2 minus 1 equals 1. And so therefore I have a true equation. It's going to be true for any point on this line. If I take the point x equals 2 and y equals 3 and plug it in, we see 2 times 2 is 4, minus 3 is 1. And yes, that point is on the line because that gives me the point 2 comma 3 gives me a true equation. Now, the point 3, 3 is not on that line because when I plug in 3 for x and 3 for y, I get 6 minus 3 is not equal to 1. It's not a true equation, right? But if I take any point that's on that line and plug it in, I end up with something true. So let's just think about that now. I'm going to do that now by taking the point, say 3 comma 5. So when x equals 3, y equals 5, and we plug it in, we end up with a true equation. What does that mean? Well, we're just going to plug these guys in. Let's see what I get. I plug in the point 3 for x. I plug in the point y, 5 for y, and I get, well, we could see that this is true, right? 2 times 3 is 6 minus 5 is equal to 1, right? In other words, what I've just written up there is 1 equals 1, right? Okay, so 1 equals 1. Obviously true, right? So let's think about this. I take a point that is on the line, plug it in, and I get something that is obviously true once we evaluate it, right? Now from there, what could I do? Well, I could take this equation right? And just say, well, if I multiply this side by 5, and I multiply this side by 5, I end up with 5 equals 5. And so that's true. Well, I can do the same thing over here because this entire thing right here is, we know it is equal to 1. It has to be because the 0.3 comma 5 is on that line, right? We're just saying here 1, it's a fancy way of writing 1, but 1 is equal to 1. Same thing that we did over here. So I could take this equation, multiply both sides by 5. And I end up with, over here, I have 1 times 5 is 5. And then I have, well, again, 5 times 1 is 5. I could do this a couple different ways. I guess I could go ahead and distribute this guy in. We get 5 times 2 is 10. It's 3 minus 5 times whatever goes in here. And we could verify, yeah, that works, right? Of course it works. I mean, you just took 1 times 5 and you said it's equal to 5. Now we're kind of writing it in a different way, and we could just verify that, yeah, 10 times 3 is 30, minus 5 times 5 is 25, is equal to 5. Yeah, check. Okay, cool. And then this is where that whole, you could multiply any equation by a constant number and you end up with the exact same set of points. This is why that's true, right? I could have, in the same sense here, said, well, at the very beginning, I could multiply this entire equation through by 5. I'll have 5 times 2 is 10x minus 5 times the negative y gives me a minus 5y equals, and then a 5 times a 1 gives me a 5. And we could have even started off with this equation if we were so inclined. Kind of like I said at the beginning, had we started here, we could move it around, and after moving the y to one side, the 5 to the other side, dividing through by 5, we would be left with that same exact equation. But that's not necessarily why it's the same line. It's just, it's really from this fact that if you have a point, say 3 comma 5, which makes this a true equation, then when you plug it into the equation, you get something trivial. You get something like 1 equals 1. So then you could multiply both sides by any constant, and the result you get will be exactly the same. So what about the case of 2 equations? Well, you have 2 equations, like what we just said was true for one equation is still true for the other equation. I could take this and multiply it through by any number, and I'll have the same set of points that satisfies this one equation. For instance, if I rearrange it and then multiply it through by 1/2, I end up getting this, right? In other words, if I take this and put it into the form y equals mx plus b, I can graph this line, and it's the line y equals negative 1/2 x plus 4. So it goes through here, 4. It has a negative slope of negative 1/2. And by the same exact reasoning we had before, I could take this, rearrange it, multiply it by any number, and any number that is on this line right here will, or I'm sorry, any point. So when I plug in a 2 and get out a 3 from here, as you can verify that's true, it will be true in here as well. And what we talked about at length is, given something like this, how to find the point that makes both of them true simultaneously. And we can verify that that point is 2 comma 3, because, well, we've already seen before, plug in a 2 here, you get 4 minus 3 gives me 1, so that's true. Plug in a 2 here, you get 2 plus 2 times 3. When I plug in a 3 for y, I get 6. 2 plus 6 is equal to 8, and so that point is on there. And so, okay, so right now this is largely review, but there's a subtle difference here, or something that you might miss, is that right now it makes sense that, well, yeah, that's the point that works, and I could verify that it works. I plug in that one point and it works. And it's kind of like saying, well, if I plug that in to that first equation, I would have, my second equation right, what we would have is 2 plus 2 times 3 equals 8. In other words, when you plug in the point that makes it true, you end up with something that's obviously true. Again, we just have something that says 8 is equal to 8. Obviously, that's true, right? So we do the same thing with the top equation, and we get something like this. We take that same special point where both equations are simultaneously true, and we end up with that. And again, that just says 1 equals 1, right? It has to be the case that you have something trivial when you plug in a point that is on both of the lines, right? So what do we have here? Well, again, we have something stupid. This just says 1 is equal to 1. This just says 2 plus 6, well, that's 8. 8 is equal to 8. Obviously, that's true, right? 8 is equal to 8. 1 is equal to 1. And so I can add these two equations together. And I get 1 plus 8 is equal to 1 plus 8. In other words, 9 equals 9, right? Obvious. But that's when you plug in a point that is true for both equations. You get something like this. And we can see why that has to be true, right? When I add these two things together, we could go through and just evaluate this. Like we've already seen what this is. This works out to be 9. That side, I'll go ahead and do that. The right-hand side is 1 plus 8, which just equals 9. We don't have to use our brains here. We know ahead of time that that's just going to give me 1 plus 8. Well, let's just see what I could do here. I mean, we have some number of red numbers, these red numbers, which are 2s. Okay, how many do I have? I have 1, 2, 3 of them. I have 3 of these. And I have 2 minus 1 of those. So we're left with plus 1 of them, right? In this case, it is a 2, that, and that's a 3. And we end up with an equation which is still true. It just still says 9 equals 9, right? 3 times 2 is 6 plus 3 equals 9, right? There's nothing crazy going on here. And really, this is what we do when we go through our method and we find, oh, x should equal 2, y should equal 3. What you do is you just go in and plug it in and check that this is all true. But I mean, this is the interesting thing that happens, right? Is when you just add these equations together, not evaluated at a point, you end up with this new equation. It's in fact a new line. It's a line that has not shown up yet. It's 2x plus 1y equals 9. And we could rearrange that and get the line y equals negative 3x plus 9, which would go through up here at 9, and it would have a negative slope. So it would be a slope of negative 3. And I'll bet you it goes through that line. I don't have to wonder whether or not it does. I already see that it does go through that line. In other words, that it goes through that point, that special point. I know it has to because of this right here. If it's true that 9 equals 9, then this also has to be true. Because when you take your point that you know works out here, right? You know for a fact that that point works. You haven't plugged in the point 3, 3, because if you tried to do that, let's see what would happen. You plug in that point 3, 3, and you add it to this point, also evaluated at 3, 3. You're going to get junk. Like that's not true because that point, well, this is not true, is it? Right? In fact, this is not true either. And so you're going to end up with junk if you try to do that. But we're not getting that, right? We know for a fact that the red point is on both lines. So we don't have to really use our brain to know that the red point will be on that. It has to be, right? Because if you look, this right here is the same thing as this. I've just replaced the red 2 with an x right there. And the y with the 3 right there, it has to work at that point. Now, the other points aren't going to work. Like for instance, 3, 5 works on that one, right? So if I take the first line, which is 2x minus y equals 1, and I plug in 3, 5, so 3 for x, 5, I get something true. That's 6 minus 5 is equal to 1. That's true. But if I tried to do that with the other one, well, that point's not on that line. And that should be pretty obvious, right? Like if I try to do that, let's see what happens. I say, okay, 3 and 5, but now I have junk right here, right? 2 times 5 is 10 plus 3 is 13. 13 is not equal to 8, right? So this kind of comes down to the issue of it must be the case that both of them are true, so that when I add them together, it has to be that the same point that worked here, the red 2 and the red 3, that works in this one, the red 2 and the red 3 works in this one. So when I add them together, the thing that I get is the same thing, it's the same formula as this, right? 3 of the first thing plus 1 of the second thing. 3 of the first thing plus 1 of the second thing has to equal to 9, has to equal to 9. And we know that it's going to work at that special point because of this right here. It's basically saying 9 still has to equal 9. At this point, we could jump right into our proof if we wanted to. It's going to look a lot like what I just did, where we had 2 equations, and we plug in a special point and show that when we add those equations, that special point also has to work. But we run the risk of not seeing a big conceptual leap that we take when we go from equations in 2 dimensions, that is with 2 variables, x and y, when we jump up to something higher. You see, when we have 2 lines that intersect, they intersect at one point, right? And we've seen that 100 times, right? In the last case, we saw it, we've seen it in a bunch of problems. We could see it graphically, it makes a lot of sense. But what about planes? See, when 2 planes intersect, they intersect in a line. And so now, instead of just thinking, and this is the risk we run, is to say, okay, so at the point where both equations are true, it'll give you, when you add them together, it'll be true at that point. But higher dimension equations aren't just true at one, or they, higher dimensional equations don't intersect in one point, they intersect in infinitely many points. So it's going to be good to graph this in 3 dimensions and see what's going on here. So briefly, we're going to talk about how we graph in 3 dimensions. So just as was the case when we have 2 variables and we said, okay, get the y by itself, and then we'll think about for any x input, we could calculate some value for y, and then we'll find the height above the x-axis for that guy, and we can find all of those points. We can find the points that it goes through for different values of x. We do the same thing here with 3 variables. We say, well, let's pick one of them, and generally you pick the z variable and you isolate that guy. So we say, okay, I'm going to solve my equation for z the same way I would if it were just x and y. So in other words, I'm going to get the z by himself by doing this right here. And here I've just rearranged the equation. And now, in the same way I had given any x, we could find the height above or below the x-axis that we're going to plot our point. Now we're saying, well, for any pair of points, x and y, we could calculate the height above or below the xy plane. What we usually do is draw the xy plane like this. We kind of flatten it out. Instead of having the y coming up like this and the x going over like this, we just kind of flatten it out like this so that the x is pointing out towards you this way. The y is pointing this way, and then the z-axis is pointing straight up. And now we do the same kind of thing instead of just plugging in points for x equals 1, x equals 2, and so on, and finding the y height. Now we don't really care about the y height. We care about the z height, and we have to figure out the different values for y as well. So what we do is we say, we tell a computer to do this, because you're going to see in just a second, this isn't going to look good at all, right? So, but it's the same principle is in play. We say, okay, how about when x is 0 and y is 1, what do we get? Okay, so when the x is 0, we're right here. And when the y is 1, then we get 0 plus 1 plus 1. We're up at 2. So we go straight up 2 units right there, and we put a dot right there. Same way as if we had an x and a y value, and we had some formula that said y equals, say, x plus 1. We plug in a 1 for x, and we go, okay, 1 plus 1 is 2. And so we go up to a height of 2 in the y. That's what we're doing right here. But now we have 2 directions to go. So we could say, okay, what about this point when x is equal to 1 and when y is equal to 1? What's the height there? Well, when x is 1, we have a minus 1. Y is 1, we get a plus 1, plus 1. 1 and 1 are 0, so we have a plus 1. So we go up a height of 1, and we put a dot right there. Go on, I'm just going to do maybe one more of these. Let's say when x is 3 and y is, let's say y is 2. So we're right here on the xy plane. It's kind of like saying, okay, choose your x and find how high you go. Now you have to choose your x and your y to find out how high you go. And in this case, we get, okay, minus 3 for x, plus 2 for y, right? X is 3, y is 2, and then we go plus 1. So then z is going to be 3 minus 2 is minus 1, plus 1 is a big fat 0. And so it's actually right there in the plane. The height above it is 0. It would be like as you're going along and you find, okay, when I plug this in, that's not that. But when I plug this in, I get a 0 for my height, right? Say when I plug in a 3, my y value is 0. Well, the same kind of thing happened here, right? We got a 0 there, and so it's right in line with the plane. But this is a bit more confusing than it needs to be because I'm not very good at drawing. So let's just graph this.
So here's our three-dimensional space where we'll be plotting our planes. We have the x-axis in red, the y-axis in green, and the z-axis in blue. Here we're graphing the plane x minus y plus z equals 1. And we can see that the points that I tried to draw on the board are accurately represented there, but this is much easier than trying to draw it on a board.
So that's what one plane looks like. Let's see what it looks like when we add in another plane.
In green, I'm graphing our second equation, x minus y minus z equals -1. And now I will put the previous plane on there in blue, and we could see that they intersect and that the intersection forms a line, right? So there are infinitely many points where those two planes have the same points, or rather, the infinitely many points where those two equations have simultaneous solutions. And they're all right there on that line where those planes intersect. There's a couple interesting things to note. If we forgot for a second that there was a z-axis, that is, if I rotated this around and oriented it in the way that I'm used to, where the x is going off to the right and the y is going straight up and down, like how we normally graph things with the horizontal x-axis and the vertical y-axis, we could see that that line right there, the line where those two planes intersect, looks a lot like the line y equals x. I'm going to try to zoom in and see if that makes it any more clear. And you could kind of see some numbers there where the numbers are getting a little bit cut off by the planes themselves. But you could kind of gauge that, yeah, that by the scale there, when you run 1, you have to rise 1 to be on the plane. That is where the green and the blue meet. Now, another thing to notice is that this line, the height where this line occurs, it looks like it's right there where z is equal to 1, right? And in fact, it's not pitched up or down. It looks like it's always equal to exactly 1 right there. That's where that line intersects. So in fact, we could even try to describe this line by saying, well, it's the line where z is equal to 1 and where y is equal to x.
So we've seen that these two planes intersect at infinitely many points, right? In fact, they form a line. And what we could do now is think about this. Let's take any point that's on that line. I'm going to choose an arbitrary point on that line. Don't let this confuse you. It's easy to think that what I'm about to do is only going to prove the case for one point. What I'm saying is we could take any point on this line, and I'm not going to specify which one. The only thing I am going to specify is that it's on this line of intersection right there. So that means that what I'm about to say is going to be true for any point on this line. In fact, it's going to be true for every point on this line. That's the nice thing about saying, we're just going to take an arbitrary point anywhere on this line. And yes, I'm drawing it out right now, but it doesn't need to live right there. It could have been this point. It could have been this point, right? It could have been any point in this line. So that's what I'm doing. I'm going to say, let's choose this point right here. Okay, then it has some x and y value. Okay, like if we looked, then there would be some x value here, and I'm going to mark that with a red x, kind of like I did before with the two-dimensional case, the red x. And then we're going to say, okay, it also has a y value, and I'm going to mark that with a red y. Finally, it has some z value. It has some height above the plane, and we can't really see where the z-axis is, but you could imagine that there's some z value right there. If I were to continue that axis, or if we could see through the plane, it would look something like that, right? And so we'd say, okay, there's some z value, and it's our special z value. So that's our special y and our special x. So that this one point that is on that line, in fact, any point that's on that line, is going to have this property that when I plug it into here, we will get a true equation. In other words, when I say, okay, plug in this special point, now what I get is, let's see, plug in my special value of x, plug in my special value of y, plug in that special value of z, and we know that when I take x minus y plus z, that number comes out to be 1. Just like before when we said, oh, 9 equals 9, or 1 equals 1, 8 equals 8. Okay, it has to be true that that right there comes out to be 1. Okay, similarly, when I plug, because, and this is the thing, because it's on this point that I just selected, that special point, is on that line where they intersect, it also works in the second plane, right? The same values. Maybe that's a 1, I don't know, a 2, and a 1, or something like that, right? Well, then when I plug it in, it will also work right here. It's a special value that works. Oops, that should be a minus. And before this gets too abstract, let's actually choose a point that works. I think 2, 2, and 1 do work. I think x equals 2. and y equals 2 and z equals 1, it should work in both equations. Let's just double check, right? So plug in a 2 for x right here, plug in a 2 for y right there, plug in a 1 for z, and let's see. That first equation comes out to 2 minus 2 is 0 plus 1 is equal to 1. Okay, so that point is on the first equation, right? I mean, it is on that first plane. Is it on the second plane? I think so. Let's check though. We have 2 for x, 2 for y, minus 1 for z still. And we get, let's see, 2 minus 2 is 0. Minus 1 is equal to negative 1. That is equal to negative 1. So that point is indeed on there. And I see where I messed up. That should have been a negative 1 right there. So basically, that's what we're saying. You take any point on that line of intersection that works. Since it's the line of intersection, it works in the first case, it works in the second case. And so we are certain that this works. And so when I add these together, let's see what happens. And this is going to be what we're going to do in general here in just a minute, but this will make it a bit more believable. We have x plus x gives me 2 x's. Minus y gives me 2 of them. Plus z minus z is a big fat 0. 1 and minus 1 is a 0. And let's see what we get. 2 of that special value of x that works, that special value of y that works. Okay. Now I'm going to clean this up. That's the same thing as 2 x's. Minus 2 y's is equal to 0. Which we could go ahead, there's a couple ways we could think about this. We could either say, well, we could solve this thing and say, okay, that's bringing 1 over to one side. We get 2 x's, 2 y's like that. And so we see that dividing through by 2, that x has to be equal to y. And that looked a lot like that line when we looked at it from above, right? Or from the perspective of the z-axis. If you're looking just at the y, the x and the y-axis, it looked just like the line y equals x. Another way we could do this is say, okay, from here, I'm going to pull out a 2. Okay. And we're left with x minus y in there. And so it must be the case, dividing that entire equation through by 2, I get the equation x minus y is equal to 0. Which, I mean, is the same thing as that right there, right? But now this is another way of thinking about it. And we could say, x minus y equals 0. Well, that's a line, but now, right, we already knew it was a line. Now we could say, well, we plug that back in there. Since that quantity always has to be 0 for any point that is on the intersection, right? Because that's, remember what I did, this is not just one point. We said this could be any point, this special x, this special y, and this special z could be any point that's on that line. Therefore, in every single case, it must be the case that x minus y is equal to 0. And so, well, then that value has to equal 0. And that value has to equal 0. When we're on that intersection, it must be the case. And so then we end up with something like, oh, z equals 1 and negative z equals negative 1. In other words, z has to equal 1. And that's what we saw when we graphed it, right? That intersection occurred at z equals 1. It was like a horizontal line as far as z is concerned, right? It was always z equals 1 right there. Notice that other points on these planes where they don't intersect don't have to obey this right here. Like in the very beginning, when I had this thing, that first equation written as z equals negative x plus y plus 1, we could take any two numbers here. I could take 7 and 5, and I have -7 plus 5 plus 1 equals -1. Z is equal to -1. Well, that doesn't match there. And X is certainly not equal to Y, but that point is on that plane. Remember, with that red X, Y, and Z, we're talking about any point where they do intersect. And there happen to be infinitely many of them. And we could see what they would look like. Z always has to equal to 1, as we saw in the graph. But X and Y could be any numbers, as long as they're equal to each other. So we could have the point 3, 3, 1. That would work. We could have the point 7, 7, 1. That would work. And just plug those in. You could see 3 minus 3, 0, plus 1 is 1. 3 minus 3 is 0, minus 1 is equal to -1. You could have the point pi over 7, pi over 7, 1. It's going to work in both of those. How about -7 over pi, -7 over pi and 1, and it'll work in both of those. So there are infinitely many points that satisfy this, right? That make both of these equations simultaneously true. Sorry if I'm beating a dead horse here, but when we only do this by graphing lines, you kind of get it in your head like, well, there is a point where it's true, and that's kind of what we're doing here. It's not really the case, because when you have higher dimensional things, when you add two equations together, there are infinitely many places where they are true. But the thing we want to prove is when you add those together and get a new thing, in this case, we ended up getting X minus Y, I'm sorry, X equals Y, that's going to be true wherever both of those are true. So when I do add these equations together, I get, let's see, 2x minus 2y plus, oh, those guys go away, and I get a 0. We've already seen this, but now we're not talking about our special point here. We're saying we get a new equation. Let's graph this equation. Let's see what it looks like.
Now we're graphing the equation 2x minus 2y equals 0 in red. And it wouldn't have mattered if I had written this as x minus y equals 0 or x equals y. Exactly the same plane would be plotted right now. You can see it's just a vertical plane like so. And the interesting thing to note is that when I add the previous equations in, we see that the red plane, which is the plane that I obtained by adding the blue plane and the green plane together, intersects exactly the same line that the previous two planes intersected.
So this new equation that we get, doesn't matter how you choose to write it, it's all the same thing, right? Because we could multiply by a constant, we could rearrange an equation, and we know we'll get the same thing. The key here is that this new equation we got went through exactly the same set of points that made both of those equations simultaneously true. So to prove this in general, we're going to need a general form of a linear equation. And what you usually see, we're not going to do it this way. What we usually see is something like this. You have a constant that we call a1. And then we say x1, that's paired with, and now usually you see a y, but in general, you don't do that. You do something like this right here. So now instead of talking about the xy axis, you're talking about the x1, x2 axis. And so instead of the xyz axis, you're talking about the x2, x3 axis. It's nice because it's kind of easy to write. The numbers match up. You could have any order that you want. I mean, any you could have go up to any dimension you want. This could be 100, this could be 1,000, whatever. You could write it like this without ever running out of letters, right? The problem is you start running out of letters if you want to say, okay, A1x plus A2y plus A3z plus, I have a lot more to do. Do I do a W? I guess I'll do a W. And how about A5 V? And then before long, you're going to run out of letters, especially if this number happens to be bigger than 26. So this is nice to do, and this is how you would see it in general, or if it's proved in a textbook or something. But this could be a little confusing for what we're doing right now. So what I'm going to say, what we do is write it like this. So we have some constant, A1. It could be any number. It's a constant number. Maybe it's 7, maybe it's negative 2.5, whatever. And then we're going to multiply that by x. Our second constant, we're going to call A2. That could be a different number. It could be the same number as A1. Doesn't matter, but that's y. Now, and we usually, what we've seen up until now is something like this. AX plus BY plus CZ equals some number, say A. But now we want to do this more generally. And what I'm going to say we want to do is, it's going to be nice if all of these in the first equation are A's, all the ones in the second equation are B's. So we're going to introduce this subscript notation here. Just remember, these are completely different numbers. You know, it's just like this kind of thing here. We're calling them something different. That could be a 7, that could be a 5, right? Just the same way that those could be different things. Now, here, we want to be able to say that we're going to do this for an arbitrary number. Maybe it's 100, maybe it's 1,000, maybe the dimension is 700 million times 700 million, but we're going to run out of letters, right? So what we're going to imagine that we've done here is that we've said, okay, A3 gets paired with some other letter, how about V? A4 gets paired with some other letter, how about W? And we go on and we go on and we keep using all these different letters until we get to the very end and we have our last one, the nth one. And maybe, like I said, maybe n is 100, maybe it's a billion, but that's the last one. There are n of them. And with that last one, we're going to call it Z. Just so like this looks familiar, right? I know what to think of. It's an x-axis and a y-axis and a z-axis. Okay, I have some kind of feeling for that. I think it's better than using the x1, x2, x3. Anyway, that's all this means, right? We have some arbitrary number, and I'm going to go ahead and forget about all these guys in the middle. We're just going to use 3 of them and just say, when I do this, dot, 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 it's understood that n is the dimension I care about. Maybe it's 100, maybe it's a billion, but we have the first one goes with there, the second one, then we haven't written them, but there's a third, and a fourth, and a fifth, and all the way up to the nth one. So that's how we're going to write it in, write a linear equation in general. We're going to say, suppose you have 2 of them. Okay, so we have A1x plus A2y plus all the others I don't feel like writing. And the last one will be ANZ equals some constant value A. Okay. We also have a second linear equation. And what does it look like? Well, it's B1x plus B2y all the way down to the last one, the nth one. And we pair that guy with z, and we say that equals some constant b. Maybe these are the same coefficients, maybe they're different coefficients. Doesn't really matter, right? Just the same way as we've had a bunch of different equations, right? This is no different. We're just trying to generalize this. Now we're going to say, suppose that there is some special point that works on here or here. And this is where it's weird. We're not just proving this for one point. In the same way that when we said take an arbitrary point on their intersection, what we proved was true for any point on there, right? So what we're going to do here, we're going to say, suppose that these things do intersect. There is some intersection. And now what we're going to do is say, take any point that is in that intersection. And we're going to give that point a special name. We're going to call it red x, y, and so on all the way down to z. So maybe it's just the number 1, 1, and just ones all the way to 1. And it's something that happens to intersect there. Maybe it's a 7 and a 2, 7, whatever, 8, blah, blah, blah. It's just that, remember, this is the special point where these guys intersect, right? I should say it is one of the special points where these guys intersect. Then, well, since that's true, since it is a point that on the intersection, then this point is on this plane, or hyperplane. It's rightly called a hyperplane. This point is on that hyperplane. This point is also on that hyperplane. So just like we did before, now we're in the situation where it's like, well, okay, so you're telling me that this is on number 1, the first one up there. Well, then it must be the case that when I plug it in, I get a1 times x plus a2 times y plus, and I keep doing that for all of the other variables until finally I get to an times z. And since it's on that plane, that's the assumption that this is in the intersection. Therefore, it is on that plane. It must be the case that that number evaluates out to a. Just like in the beginning, it's like, oh, 1 equals 1. Yep, okay. So that's all we've done. We've plugged it in, and now we have something that says a is equal to a. Big capital A, sorry. Okay, now, okay, this point makes both of those true, right? So it's also a point that satisfies that equation. And so when I plug it in, I get b1 times x plus b2 times y plus, and I do all of the others, and I finally get down to bn times z. Well, it must equal b, because that's what it means to be on that hyperplane. And when I plug those numbers in, we get whatever that evaluates out to does equal the number b. Okay, so we're right back to our, like, what we talked about at the beginning. Now we're in the situation where you have 1 equals 1 and 8 equals 8. So it must be true that when I add them together, I get 9 equals 9. Because what have I done? I've taken a bunch of numbers, plugged them in, and by assumption, it's like this solves that. It is a point that is on that plane. Therefore, I plug it in and I get a equals a. Ditto for the second one, b equals b. So when I add them together, what do I get? Well, kind of like we did before, right? You say, well, you have a1 of those and a b1 of those. One way of thinking about it, if you like, you could say, well, a1 times x plus b1 times x. If you like, we could think about this as we're going to factor out that x. And what do we get? Well, the x pulls out and we get a1 plus b1, just like that. And that's easy to see, right? Because if it were, say, 7x on the top and I don't know, 2x on the bottom, we'd say 7, 8, 9, 9x's, which is the same thing as saying, oh yeah, what did you do? You took 7 plus 2 right there. That's all we're doing. That's all we're saying right here is that. Add that plus that, and that's what you get. A1 plus B1 times X is what you end up with. Plus, okay, if that's a 5 and that's a 2, you'd say 5, 6, 7. You would do the addition, but we don't know what they are. So we'd say, well, do the addition, A2 plus B2. And then whatever number that happens to be, you would take that and multiply it by Y. Yep, okay, plus, boom, 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 boom. All the way up to, and we say, oh, okay, you have, say, 4z and negative 2z. You'd say 4 minus 2 is that. Well, what did you do? You added those two numbers together, right? an plus bn times whatever z is equal to, finally, a plus b. Again, we know that that equals 1 plus 8, right? We know that that equals 1 plus 8, and so it has to equal 9, right? That's all we're doing right here. Saying whatever, if that's equal to A and that's equal to B, then when I add those together, it has to equal A plus B. But now we're going to just stop and say, wait a minute, let's pretend that we didn't do any of this. Let's pretend that we just had two equations, just general equations. Just general equations, and all we did was add them together. Because that's what we've been doing for the last however many weeks now, right? We'll just keep adding these equations together and hopefully everything works out. Well, that's what we're going to do here. We're just going to say, okay, just take this and add it together. What do you get? Well, whatever those coefficients are, I would have A1 plus B1 times X plus A2 and B2 times Y plus all the way down. We do all of the variables until we finally get to the last one, an plus bn, whatever those coefficients are, times z equals a plus b, big A plus big B. And then we say, okay, so stop for a second. We took two equations, we added them together, and we got a new equation, right? We've seen this before, like in the first thing, we added those two equations together and we got like 3x plus 9. It was a new equation. It was not the same line. We've added two hyperplanes together. They're not the same plane, but in this thing, I know for a fact now that if I plug in that special number, what happens? Well, let's see. We take that number, plug it in for x, we get that. Take that number, plug it in for y, we get that. We can be certain that it does give us this right here. In other words, like if you go back to the beginning of this video, that's exactly what we did, right? We said, well, wait a minute. We know that this point already works in that new equation. So that's our proof. That's what we were trying to prove, right? We said, suppose that there are two hyperplanes or lines or planes or some kind of objects that do intersect. Okay, they have an intersection. That is, there are points, possibly infinitely many, that satisfy both of them at the same time. Okay, so I took any one of those points and said, well, take any one of the points that does satisfy that, right? That makes both of them simultaneously true. Then you get two true equations, you add them together and you get this true equation. It must be true because that's the hypothesis, right? It's like, if this makes both of those true, then when you add two true equations together, you get a true equation. Then we see, well, wait a second, that's the same thing as saying you have two equations and you add them together, you get a new equation, you get a new line or a new plane or a new whatever. And what this means is, well, wait a second, this was true for every single point that these both went through, right? Just like with the planes, we have two planes, we have a line with infinitely many points, and we say take any point on that line and it will be the same, it will make the new equation that you get true. You'll get a new plane when you add these together, but every point that satisfied the previous two simultaneously, in other words, every point in their intersection, the new thing that you get goes through that same intersection. So you can see why I said it's not very satisfying when you just, like, if I just wrote this up here, it'd be like, but after seeing it graphed, you kind of see what I mean. In the one or in the two-dimensional case, there's 1 point. And so it's like, well, yeah, obviously that 1 point works. I could see that, but it's hard to imagine what I mean by saying, by saying take any of the infinitely many points where both of those are true. But now you have like an image in your head of two planes intersecting in a line. You could say, oh, you take any point in that line, and the new thing you get will also work out at that point. So it has to work for every single point. And we've actually seen that, right? Because when you take those two equations and you add them together, you get a new plane that goes through exactly the same points. What I want to do is try to convince you of all that I just said by going through a problem from the homework and graphing it as we go along to see what we're doing here. X plus y plus z equals 6. 2x minus y plus 3z equals 9. Minus x plus 2y plus 2z equals 9.
Our system that we're graphing, I'll show you the first plane, x plus y plus z, looks like that in the plane. Our second equation, 2x minus 3y, 2x minus y plus 3z equals 9, we're going to do in green here. It looks like that. And you can see that the intersection of those is a line, right? That on that line, those are the points in 3D space. In other words, the pairs x, y, and z that satisfy both of those equations simultaneously. So we have our first equation in red, our second equation in green, and in blue, we're going to do our third equation, minus x plus 2y plus 2z equals 9. Right there. Now we can see that each of the planes actually intersect pairwise. Pick any two planes, they intersect in a line, right? We can see the blue and the green intersection there. And we can see that the blue and the red intersect right there in a line. And that line itself intersects the green plane. The blue and the green planes intersect in a line. That intersects the red plane. And so on, right? The red and the green, they have a line and they intersect the blue plane. And it looks like where those three intersect is somewhere here in the first octant instead of a quadrant. When we have octants in space, it looks like it's right around there. But you can see, even if you can graph this, trying to find that point is going to be quite difficult.
So to solve this system, we are going to put it into a matrix. We'll have 1, 1, 1, 6, 2, negative 1, 3, 9, negative 1, 2, 2, and 9. Now, instead of, I normally like to get both of these zeros in one step. Since we're trying to see how these planes change as I do this, I'm just going to do these one at a time. So to get a 0 here for the first one, I need a negative 2 to add there. So I need a negative 2 right here. So I'm going to multiply the entire top row by negative 2. If I wanted to, I could graph that, and that's not going to change it. It would be the exact same thing. Now, let's go ahead and add them. We're going to keep the top row, not changing that, not changing the bottom row. Okay, so negative 2 and 2 gives me 0, as expected. Negative 2 and 1 gives me a negative 3. Negative 2 and 3 gives me a positive 1. Negative 12 and 9 gives me a negative 3.
So since we're adding the first two equations together, let's just look at the planes that those equations define. We have the red is the first equation and the green is the second. And when we add them together, right, in the way that we did, we got a third equation, negative 3y plus z equals negative 3. And let's see what that looks like. I'm also going to do that one in green. And you could see that it intersects the exact same line. In other words, like we were saying earlier in the video, any point that satisfies both of those equations will satisfy the new equation that we got. So in other words, any point on that line where those first two intersect right there, that new one is going to have to go through that same line right there. And that's exactly what we see. So this is our original system, and we could see that point where all three planes go through there in the first octant. We just look down that blue and green line and see where it intersects the red right there. What I'm going to do now is look at our new equation we got. right here. And we can see it goes through that same point. And of course it has to, right? Because we could see that the original ones, get rid of that guy, the original ones, if we look at the line that the green and the red planes form, and we see where that thing intersects the blue, it's right in there somewhere, right where those two guys cross, right? And then when I add my new equation in that I got, see it goes through that, since those go through the same line, it's got to intersect that blue plane at the exact same place. So now we're going to get rid of our old equation. Now we have our new system. And this is the system that in our second matrix right here.
To get a 0 right here, well, I don't really need to do anything. The 1 is already there. That's what I need to kill that guy. So I'm just going to add that one to that one. And so the top row is not changing. We still have a 1, 1, 1, 6. The second row is not changing. 1 minus 3. Now the bottom row, 1 and -1 is 0. 1 and 2 is 3. 1 and 2 is 3. And 6 and 9 make 15.
Now we're taking the first equation, or the red plane, adding it to, or a multiple of the red plane, and adding it to the blue plane to get a new plane. And let's see what we get. So when we did that, we got 3y plus 3z equals 15. Let's see what that looks like. And you could see, yep, that new plane, it's slighter light blue, right? But it's going through the exact same line that those two planes define, right? The intersection of those two planes, the new plane goes through exactly the same line. And everybody here, we could see that, yep, the place that the other ones intersected, that green plane, well, that's going to be the same line as the original one right there. Or the new line that we get will be in the same place. Now we have a new system, but the common point where those all had in common here in the first octant is still the same point, because all we've done is all of the lines that defined where those points intersect, we haven't changed any of those. It's still going through the same lines. It's just that the planes are a little bit, they're oriented a little bit differently. They have different slopes, if you want to think about it that way. Okay, but we're still aiming at that same one point right there.
Now, if I were doing this, I would probably flip these and make that my leading one, bring that up to there, but we want to keep these in the right order so we can see how these things change with each step. So I am going to just get a leading one in this position by dividing this entire thing by -3, multiplying by -1/3. So that gives me a 0, a 1, a -1/3, and a 1. That does not change the picture, right? That plane is exactly the same as that plane.
So that green plane, as I'm graphing it right now, is -3y plus z equals -3. And we could see that if we were to change that, y minus 1/3 z equals 1, it didn't change the plane at all. That's what we expect, right? We just multiply that same plane by some constant number, and it doesn't move it whatsoever. The same points are right there.
Now I need to get a 0 right here, so I need a -3, which means I need to multiply this entire row by -3. That gives me a -3, a +1, and a -3. When I add that to the bottom row, well, the top row is not changing. The second row is not changing. Now the last one, we get a 0 and a 0, a 4, and 15 minus 3 is 12. Okay, so now we have a new plane. We could graph it as 4z equals 12, or we could go ahead and get that 4 out of there, get a 1 there like we want in our algorithm, and we'd end up with the exact same picture.
We're going to add a multiple of the green plane to the blue plane, and what we should get is something that doesn't change that intersection, that line right there of the green and the blue. Let's check that that's the case. There's the new plane. And right now I'm graphing it as 4z equals 12, but we don't need to write it like that. We could write it as z equals 3, and we could see it's the exact same plane that way. It's just now it's oriented in a way that's going to help us out a lot. Okay, so still going through the same line, intersecting the total, that original point that we're interested in, it's still intersecting that original point where all three are in common.
Now, to get rid of that negative 1/3, I need a positive 1/3, which means I need to turn that into a positive 1/3. So I'm going to multiply the entire row by positive 1/3. That gives me a 1 right there. When I add that to the second row, okay, the bottom row is not changing. Top row is not changing. Now I add 0 and the 1 and the 0, and finally 3 and 1/3 and minus 1/3 gives me a 0. 1 and 1 give me a 2.
So we combine the green plane and the blue plane together to get a new plane. That plane works out to be y equals 2. And we could see that, yeah, it goes through the exact same as the originals, right? We haven't changed the line that's common to them, right? So now this is our system. And we're still aiming at that one point that we're trying to get at right now.
Let's continue on here to get all my zeros going up. Now, I need a -1 to kill that guy. So I multiply that entire row by -1. Gives me a -1 and a -3. Add that to the top row. Now the bottom row is not changing. The middle row is not changing. Adding that to the top row gives me 1, 1, 0, right? Because 1 and -1 is 0. And then 6 minus 3 is positive 3.
Then we combine the blue plane and the red plane together to get a new one, which is x plus y equals 3. And we could see that, yep, that goes through exactly the same line right there. So we'll get the old one out of the way.
Last step, I need to basically, I could subtract this row from that row. You can think about that as multiplying that row by -1. That gives me a 0, a -1, a 0, and a -2, which I add to the top row to give me, well, hold on, the bottom row is not changing. The middle row is not changing. Now the top one, I'm going to add there, we get the 1. The 1 and the -1 make a 0, and then 3 minus 2 is 1. So we find that x is equal to 1, y is equal to 2, and z is equal to 3. And those are the 3 planes that now obviously identify the point that we want.
Finally, we're going to combine the red plane and the green plane. Those two, that line right there, to get the equation x equals 1, which, what do you know, still goes through that common intersecting line right there. And finally, our system has turned into x equals 1, y equals 2, z equals 3. And we could see where those planes, finally, that common point that's right there in the first octant is easy to find. We could say, well, let's see where the y, where that plane goes through the y. It's actually kind of hard to see, but but the red plane, which is the x plane, goes through 1 right there. The y goes through 2 right down there. And the z goes through 3 right there. And that is the point where all of those guys meet up. Right there. 1, 2, 3.